had to break out my favorite song for the last video of the year here. I had to break out a little radioactive for you. But we got a really nice theme here tonight before we come tackle a big bear tomorrow, and we're going to talk about trig equations. And I just want to go over one brief notational issue here that I think is one of the trickiest things. Is that when you see sine squared and they put the squared where they do, you're really taking the entire quantity sine of x and squaring the result. You're not squaring the angle, you're taking the sine of the angle and then squaring the result. But that's just one little thing as we go forward here. The first thing is I want to introduce a first degree linear, what I call a linear trig equation. Let's talk about 2 sine of x plus 1 equals 0. Let's assume that our domain is from 0 degrees up until 360 degrees, and we want to solve for all the angles. Now you notice there are no squared signs, and that's why I call it a first degree. So what I'm going to do is I'm going to subtract the 1 over, and then after that I'm going to divide by 2. So we just really want to isolate that sine of x, get that rascal by itself. And what we do here is we're going to identify a reference angle, and that's basically the angle that you've memorized. And we know that the sine of 30 degrees is equal to 1/2. Now in this particular case, 1/2 is not a solution, it's just my reference angle. And what we're going to do is we're going to identify the 2 quadrants that sine's negative in. And I identified this third and the fourth quadrant. All I'm doing is I'm visualizing the old acronym, all students tip cows. And so we know sine's negative here in the third and in the fourth. And so the third quadrant, I'm thinking 180 degrees plus 30 gives me a solution of 210. And then in the fourth, I'm thinking 360 minus 30 gives me a solution of 330 degrees. The only other bear trap to watch out for is if maybe they change, they want the answers in perhaps radians or something. But I think we're pretty good at that. Here's a much bigger rascal. Now this equation is what we call a second degree trig equation or a quadratic trig equation because of the squared sign. And we're just going to go ahead and factor, at least, kind of cross our fingers and hope that it's factorable, and I believe that this one is. So we've got sine of x times sine of x, and then we're just focusing on 2 numbers that add up to -4 and multiply to -5. And I'm feeling a -5 here and a positive 1 there. We've got it factored perfectly. It cooperated very well. We're going to tee this bear up. We're going to set each of these quantities equal to 0 and solve for, let's see here, add the 5 over. Now this one doesn't exist. There are no solutions because as you visualize the sine curve, it never gets higher than 1. So reaching a height of 5 is impossible. We say no solutions. And then we come over here and we say that the sine of x has to equal -1. Again, visualize that sine curve. And -1 occurs at 270 degrees, or you might call it 3 pi over 2. In this particular case, we would have to say 270 because the domain was given in radians. Or, I'm sorry, degrees. Couple of reasons I chose this next problem here. First of all, it is a quadratic trig equation, but they threw in a coefficient of 3, which makes our factoring significantly more difficult, and that's if it even is factorable. The other thing is they used a weird Greek letter called alpha here as the variable. You don't have to stay with that. You could change that to theta, you could change it to x, any particular variable that you feel more comfortable with. So here's what I'm going to do. I'm just going to rewrite it so that it is in terms of theta. For whatever reason, I feel a little more comfortable with theta. Maybe you felt better with an x. And then, in fact, with that being said, when it comes to factoring, if you want to go off to the side and just rewrite the quadratic as 3x squared plus 14x plus 8 and try to factor that first, then that, be my guest. You go 3x and an x, and you're thinking I need multiples of 8. So I'm going to put the plus 4 here so that the outer multiplies to 12. And that would leave me with a 2 here. So outer plus inner does add up to lucky 14 here. So I'm just going to bring that over, and I'm going to say it's really 3 sine of theta plus 2 and sine of theta plus 4. And if you ever have any doubts about your factoring, you can always FOIL those 2 binomials together right here and see if it does produce the original trinomial. We're now ready to tee it up, our favorite part, and we're going to say that the sine of theta has to equal -2/3 because we subtracted 2 divided by 3. Also, the sine of theta equals -4. I'm going to tackle this one first because, again, when you visualize that curve, it never reaches a height of -4, so we say the solutions do not exist. There are no solutions. You come over to this side. What we're going to do is we've got to get a reference angle. I'm going to use my calculator to help me because 2/3 is not a famous value that shows up on my table that I memorized. And then we're also going to identify the quadrants here. We're going to say, again, quadrants 3 and quadrant 4 is where it's negative. So I'm just going to grab my calculator and I'm going to do inverse sine of positive 2/3. So I'm actually going to make a little note of that right here. I'm doing, on my calculator, inverse sine of positive 2/3, and that's going to give me my reference angle. As I typed that into my calculator, I got a reference angle of 41.8, rounding to the nearest degree that they requested, or nearest tenth of a degree that they requested. Let's see, for the third quadrant, we're thinking 180 plus that reference angle. So let's see, what does that throw us at? That's at 221.8 degrees. And then I'll do 360 minus that reference angle. And that's going to put me at 318.2 degrees. So those are my two solutions right there, the only two. All right, we're coming down the home stretch here. This is a sneaky one. It doesn't look like it's quadratic, and in fact, it's not because there are no squared signs. But what kind of factoring technique would you tackle here? And that's the big question. Hopefully, you're screaming GCF. You'll notice this is one term. This is your second term. The plus sign separates them into two separate, distinct terms. What do they share in common? They both share a sign of x. And so I'm going to factor that out, and I'm going to divide the first term here by sine of x, which leaves me with 5 cosine. And then I'll divide the second term by sine, which leaves me with a plus 2. And again, if you have any doubts or hesitation about your factoring, just distribute the sign back through and see if it leads you back to where you started. Nonetheless, I'm feeling pretty good, so I'm going to tee it up. Say sine of x is equal to 0, or cosine of x is equal to negative 2/5, kind of an interesting one. Draw your curve. You have a height of 0 at 3 different locations, 0, pi, and 2 pi, or if we're working in degrees, it'd be 0 degrees, 180 degrees, and 360 degrees. And then for the other one, we're going to have to say I need a reference angle, and then we're going to be negative in the second and the third quadrant for cosine. Again, I'm just going to grab my calculator here and do inverse cosine of positive. As I did inverse cosine of 2/5, I got a reference angle of 66.4. We'll just go nearest tenth like we did on the last one. If I do 180 minus that reference angle, I got 113.6, so there's another solution. And then 180 plus 66.4. Let's see, that's 246.4. So I've actually got 5 solutions. Look at this, 5 big solutions. Our last one for the night is a big rascal, a question that we'll see either a part 3 or part 4 caliber question on the exam. And the trick is because they're trying to hide a double angle on you. They tried to sneak in this double angle within this entire equation here. And so anytime you see a double angle, we need to instantly substitute for it. What makes this one a little more challenging is when you go to your reference sheet, there's 3 different options for cosine a double angle. It's not as straightforward as sine. So we're going to pick the one. You'll notice the rest of the equation is in terms of cosine. So I'm going to pick the double angle formula that's also in terms of cosine. So I'm going to use 2 cosine squared, in this case a. I just want to be consistent, use the same variable all the way through, plus 1. And then I'll just rewrite the rest of the equation here, plus 5 cosine of a plus 3 equals 0. Whoops, we just caught a little mistake. This needs to be a minus sign in the middle. 2 cosine squared of a minus 1. Again, straight off the reference sheet. Now we're going to clean this up, and we got 2 cosine squared of a plus 5 cosine of a plus 2 equals 0. We're just going to factor that really quick, and we're going to go 2 cosine of a times 1 cosine of a. I don't really need the 1 there. I'm going to throw a plus 2 here and a plus 1 there so that my outer plus my inners add up to 5. We're good to go. We tee this rascal up. We're going to get cosine of a equals negative 1/2. And then we're going to get cosine of a equals negative 2. That one doesn't exist. Curve never has a height of negative 2. Here we've got a reference angle of 60. And then as we go to, let's see, one's cosine negative. Second quadrant would be 120. Third quadrant would be 240. There we go, rock and roll. So here's your extra credits tonight. I think some of these are going to be snappy and others are going to take a little bit more work. We've got question number 1 up here is a multiple choice question. Show us some work to convince us of your answer. Number 2 is also multiple choice. And then we've got 3 open-ended questions here that will use the same set of directions right here as far as solving to the nearest tenth of a degree within the interval 0 to 360. So everything's in degrees tonight. Let's see, 4 and 5. So good luck with these tonight. And I tell you what, you guys have had a tremendous, great year. And all of your hard work's going to pay off tomorrow. And I wish you all the best of luck.